In this video, we're going to discuss visualizing functions of two variables. In particular, we're going to talk about two ways to visualize functions of two variables, f of x, y equals z. We're going to use level curves and contour maps, and we're also going to sketch the surfaces themselves. Now, many of the functions of two variables that you're going to see in this class are just the surfaces that we discussed when we just talked about cylinders and quadric surfaces early on in the semester. So hopefully you recognize this. F of x, y is just another name for z. Now that is, I've got x and y both squared, z is raised to the first. This is an elliptic paraboloid. But now let's think of it a little differently. I'm thinking of it as a function of two variables. Now every x, y in the domain of this gets mapped to a z value. So if x and y are both equal to 0, well, I get when x and y are 0, z is equal to 0. So we have this point right here on our graph, 0, 0, 0. Or when x and y are both equal to 1, well then z is 1 squared plus 1 squared, that's 2. So this point, 1, 1, 2, is also on the graph of our surface. But when y is equal to 0, we get z equals x squared. We know what that looks like. When x is equal to 0, we get z equals y squared. We know what that looks like. And so when you put those two together, you get this. So often in our class, when you're graphing a function of two variables, it's just going to end up being one of those functions that you talked about, that we studied before, one of our quadric surfaces or cylinders, and you're just getting z by itself, and then you're sketching it. So this is one way that you can do it. You can just sketch the surface, and those surfaces are going to be functions that you're already familiar with sketching. Now we could also sketch surfaces using level curves or contour maps. This is particularly important when it's not one of the surfaces that we've already studied. But if it is one of the surfaces that we've already studied, I think it can help us understand the concept a little bit better by applying level curves and contour maps to visualizing something like this. So that's what we're going to do next. Let's say I want to find, or I want to think about this surface and visualize this surface not knowing anything about what it looks like. Maybe I haven't studied elliptic paraboloids yet, and I'm just trying to get some sense of what's going on with the surface. One way that we can do that is we can sketch what are called level curves. A level curve is just going to be a curve in the xy plane it's found by setting z equal to a constant and then just rearranging the equation. And we want to set z equal to a constant that's actually in the range of the function. So if I set z equal to -1 here, I'm going to be out of luck. I'm not going to be able to graph x squared plus y squared equals -1. So I need to pick a z value that's in the range of this. If I'm taking a real number, I'm squaring it, and taking another real number and squaring it, and then adding those together. Well, these are all non-negative numbers. They're always positive except for when they're 0. So are these. So when I add them together, I'm going to get a number that's positive or possibly 0, just like we see here. The z values, the lowest z value is 0, and then they just go on to infinity. This goes on forever and ever. I just can't draw it forever, so that's why we draw it with a top on it like that. So I pick a z value in the range of this, and the range for this one, just because of what I know about real numbers, that's a non-negative number, that's a non-negative number. I add them together and I get a non-negative number. So I pick a z value in here, and then I set it equal to this, and then I sketch my curve. So I'm going to choose z equals 0, z equals 1, z equals 2, z equals 3 and z equals 4. Now the easiest ones to sketch are going to be those with perfect squares for z equals 1, z equals 4, and z equals 0. But I want to sketch z equals 2 and z equals 3 for a good reason, and I'll explain in just a minute. So set the z value, f of xy, equal to that number, and then graph the resulting curve. So I've got 0 equals x squared plus y squared, 1 equals x squared plus y squared, 2 equals x squared plus y squared, 3 equals x squared plus y squared, 4 equals x squared plus y squared. It's probably going to be easiest to graph that one, and that one. So we're going to graph them now. Okay, so we're graphing them in the xy plane, graphing the resulting curves. Now the only way we're getting 0 out of this is if both x and y are 0. So we've got a single point, 0, 0 right here. So the level curve in this case is degenerate. It just reduces to this single point. So at this point, I'm just going to label it z is equal to 0. Now this curve is a circle of radius 1. So I'm going to draw a circle of radius 1. So that's a 1 and that's a 1. On that curve, z is equal to 1. So you might think of this like a topographical map. Z equals 0 is right there, and z equals 1 is 1 unit away, and then it's up 1 unit. So imagine that that is raised 1 unit out of the page. So it's a circle of radius 1. And this one is a circle of radius square root of 2. This one is a circle of radius square root of 3. This one is a circle of radius square root of 4, which is 2. I'm going to graph this one, and then we'll graph the other two, just to get a better sense of what's going on. So here's my circle of radius 2. Trying to do a decent job drawing it to scale, but you know, we do the best we can. And this is on this curve, z is equal to 4. So if this is in the page, that's 1 unit out of the page, and this is 4 units above the page. Now square root of 2 and square root of 3, and I forgot to mention all of these are circles centered at the origin. I think you knew that, but just in case you didn't. These are centered at the origin, and r squared is this number, so r is the square root of that number. Square root of 2 is approximately 1.4, and square root of 3 is approximately 1.7. Okay, so I'm going to try to draw curves that circles with radius 1.4 and 1.7. So here's one that's radius 1.4 approximately. And here's one that's radius 1.7 approximately. Now if I did a better job graphing this, you would see it a little bit better. So there's z equals 0, z equals 1 is here, z equals 2 is here, z equals 3 is there, z equals 4 is there. Do you see how these guys are getting closer together? The gap between that degenerate circle of radius 0 and the circle of radius 1, that radius is 1. There's a 1 unit gap there. But the gap between this radius and this radius is 0.4. And the one between this one and this one, it should be 0.3. I didn't do a very good job showing you in the picture, but it should be 0.3. And this one should be about 0.3. It's actually a little bit less than 0.3 because that's not really 7.3 or 1.7. It's about 1.73 approximately. So that next jump up is about 0.27 approximately. So what does that mean? Well, if this is farther away from this one, that means the z's are increasing from 0 to 1 over a longer distance. Here the z's are increasing from 1 to 2 over a pretty short distance, from 2 to 3 over an even shorter distance, and from 3 to 4 over an even shorter distance. So the fact that all of these are evenly spaced and all of these level curves, and these are called level curves, they're not evenly spaced, tells us that our z's are increasing more faster. The z's are increasing faster as we go from this level curve to this level curve. Or let's look at the corresponding curves in our 3D picture. Z equals 0 is down here. Z equals 1, that's a circle of radius 1, that's right there. The next one up is a circle of radius 2. The next one up is a circle of radius, or that's radius square root of 2. The next one's a radius square root of 3. The last one is a radius square root of 2. And this is at Z equals 1, 2, 3, and then 4. Do you see how much faster Z is increasing over here than it is down here? The Z's are increasing over a much larger distance here. They're going from 0 to 1, but they're taking their time. Here they're not taking their time at all. That Z is just climbing and climbing and climbing. It's a consequence of that squaring function in each of the directions, in the x direction and the y direction. So this level curve, even if we did not know what this looked like, will allow us to infer something about this graph. I imagine that's at 0 units, and that one's at 1 unit, and that one's at 2 units, and that one's at 3 units, and that one's at 4 units. And so I can sort of see, if I'm imagining all of those points coming out of the page like that, something that looks like this. Now, I will have you graph level curves, and I will have you graph surfaces that we've studied previously, but I won't have you graph any really truly different surfaces that we haven't already studied using this method. Like, I wouldn't be able to go from a traditional topographical map to drawing you a mountain range. It's difficult to do. But I might have you take a level curve and then match it to the corresponding graph. I believe I have assigned problems like that in the homework. Okay, so that's how we visualize our functions of two variables. Started with this simple example of level curves in this, sketching the surface in three-dimensional space. The ones I'll ask you to graph are going to be parts of surfaces we've studied previously. Those level curves that I ask you to graph, they're going to tend to be conic sections. So you're going to see a lot of circles, ellipses, hyperbolas, parabolas, and occasionally you're going to see just lines and curves that you've studied in college algebra prerequisite classes. Now, when I put all of these level curves together on the same map, we call this a contour map. And again, it behaves kind of like a topographical map. I'm imagining, I think our textbook uses the letter C instead of Z. I just call it Z because that's what it is. You're imagining this is it's at 1 unit into the page. This one's 1 unit out of the page. This one's 2 units out of the page. That one's 3 units out of the page. And that one's 4 units out of the page. And so you've got this surface sitting on top of this and coming out at you. That's giving us that. So that collection of level curves is called a contour map. Excuse me. We'll do more examples like this in the next video.